Hello and welcome. We are the Cal Poly Pomona Ponderosa Team 2020 that participated in the control section of the overall project. Our team consisted of 5 members: Justin Law, our team leader, Paul Locher, Kevin House, Robert Smith, and myself, Gilbert Melecio.
Our goals. Our goals are to design a new robotic arm control system to automatically ping Christmas wreath. By doing this, we will increase productivity of the supply line for the Boys Republic. We'll be enhancing the existing motion control system, also designing and developing a control system for the fluids, and finally implementing programmable logic control based on a human-machine interface. Client's background. Our client is Boys Republic, which is a private nonprofit school treatment community that helps adolescent youth by developing their academic, social, and vocational skills. They introduced Della Robio's REAP program in 1923 to serve as a work experience for students. Over the years, it has become one of their largest fundraisers for the school, selling around 50,000 REAP worldwide. New design, enhancement of motion control. On the left, we have last year's algorithm state machine chart. On the right, we have our new design of motion control. New design 2020. Our new design implemented a flow level sensor to detect the flow and level of fluids, Hall effect sensors to limit the three axes, a programmable logic control based on human machine interface for the user, encoders to track position and velocity, a printed circuit board for distribution of power, and a redesigned motion profile to eliminate step skipping. Original design objectives. Our objective is to create an entire closed loop system, implement a user interface, design a printed circuit board for power distribution and single flow of general purpose input and outputs, introduce Hall effect sensors to limit the three axes, implement encoders to track the position and velocity, and finally redesign the motion profile to eliminate step skipping. COVID-19 mitigation efforts. Due to COVID-19, we had to switch to a virtual environment using Copelia Sim to simulate the robot program with controls and computer vision. We'll be providing Boys Republic with code and printed circuit board files.
The control system block diagram is comprised out of a PLC, Jetson, and PCB. The inputs are in gray while the outputs are in red. The PLC receives data from the flow and level sensors and displays it onto the HMI. That data is passed on to the Jetson, telling it to continue operating or to pause. The Jetson controls motor movement and spray, also receives data from Hall effects and encoders, providing feedback to the control system. The user interface was built using a Kinko PLC and touchscreen HMI. The purpose is to provide start and stop functionality to the system, shut down the Jetson, and level and flow rate data display. An extension of the flow and level data display is the alarm frame, displaying instances of low level and flow rate to alert the operator of a problem. This level is defined as less than 20% of the maximum. The PLC ASM operates as so. When start is pushed, the PLC outputs a 1, telling the Jetson to start operation. After a short delay, the fluid data is checked. If it's under 20%, operation is halted by setting the output to 0. If not, the output is left at 1 and the loop repeats. PLC to Jetson communication is done by dropping the 24-volt digital output of the PLC to 3.3 volts through optic couplers providing voltage isolation. The output of the optic coupler will then be connected to the Jetson's GPIO.
Here is a quick demo of our HMI and PLC, using a battery and potentiometer to represent the voltage acquired from the flow sensors and fluid level. You can see the displays and bars show the data acquired from the ADC unit. The start button enables the 0.0 output while the stop button disables it. The 0.0 disabled. The off button pulses the 0.1 output for 2 seconds, telling the Jetson to turn off. 1, 2. When the flow rate or the fluid level are too low, a buzzer will trigger and the alarm will be displayed while also setting the output 0.0 to 0. It's set to 1. Our flow and tank go too low. The alarm triggers, showing it here, and on the alarm page it'll tell you exactly what happened, and our output is deasserted.
This is the ASM chart for our system. To give a general overview of the chart, we start the system up, and once powered, all the motors automatically move to their home position. From there, the Jetson checks for a signal from the PLC to start moving. If there's no signal from the user through the PLC, then the system will stand still. During this time, the CV is feeding us data based on the size of the wreath, which will adjust the Y motors accordingly. We then wait for CV to start tracking the wreaths, and once it has tracked, it follows and sprays the wreaths. At the end of the cycle, it returns to its home position 50% faster to make sure it doesn't miss the oncoming wreaths. A key step in making this happen is the motion profile. We redesigned the motion profile to eliminate the skipping of the X motors using an S-curve. We created an S-curve by solving for acceleration directly instead of time. We turned time into a ratio based on the desired curve characteristics. By this, I mean we distributed 75% of the time for the linear portion, and the other 4 segments are 6.25% distributed each. Once we calculated the ramp-up acceleration, the rest was easy to figure out. That's enough of the theory, so let's go into how we applied this to our project. We calculated the total time by using the distance in inches of the robot over the velocity acquired by the computer vision. We applied this to our system using the velocity values acquired by CV. From each distributed segment, we translated them into delays, which are then stored into an array so we could use them later. All we really needed to do was find the ramp up data so that we could store it and reverse it later. As you can see, the speed of the motor directly relates to the voltage output. You can also realize, probably not in this video, but there will be links to this video, that the sound of the ramping up and ramping down are different.
This is the circuit used to operate the solenoids. The L and the R component represent the characteristics of the solenoid. The MOSFET is used to switch the solenoids on and off. The pulse generator coming into the gate represents the GPIO pin of the Jetson. This allows us to activate the solenoids at will. The flyback diode is used to provide a path for the self-induced voltage coming from the inductor. Below is a simulated waveform where the green is the pulse generator and the purple is the current through the diode. As you can see, when the MOSFET is disabled, the solenoid will generate current back to the diode, which peaks at 1 amp. Peaking at 1 amp forces us to use a diode that is capable of handling this current. Thus, the diode D1N4148 must be changed to a Schottky diode, which can handle more current. Here's the code for counting encoder pulses to track position. This increments a count on a rising edge. This is done through 2 pulling latches that must be satisfied before a count is added. Since this is a multi-threaded action, data is saved in the structure which will enable us to access the counts in the main thread. This is a demonstration of the Y motors with encoders. Here the buttons represent encoders. When the button is pushed, a pulse occurs because we are using dual Y motors. In order to ensure that both motors are stepping at the same rate, the encoders will be compared. If one motor leads the other in steps, the program will step the lagging motor and halt the leading motor until the encoder's counts are synchronized. Here's a demonstration. The Y-axis encoder is velocity controlled. The block diagram shown below represents the sensor feedback. The encoder pulse provides a square wave. The F to V converter converts the frequency of the square wave into a DC voltage value. which is then read by an ADC using I2C protocol. In the program, the Jetson will translate the voltage into a velocity value. Here is the code we use to operate the ADC using I2C protocol. On the left is an image of the code, while the bottom is a schematic of how we will hook up the ADC in a PCB. This slide shows where the Hall effects are going to be placed so that the motors know where home position is located.
FV converter schematic. The top schematic is the FV converter. Using an LM331 chip, an input frequency from the encoder is turned into a DC voltage output. An LM324 quad op amp filters this output to between 0 to 6 volts. This sets the speed of the motors, with 6 volts being the minimum speed and 0 volts as the maximum, with code reconfiguring this output as a positive slope. The reference voltage of the LM331 is 6 volts to enable dual supply for the op amp from a single 12 volt supply to a low current 6 volt dedicated plane on the PCB. The schematic at the bottom shows one of the op amp sections is configured as a buffer with a resistor divider network to drop the 12 volt input to an output of 6 volts and prevent loading. Controls computer vision communication. Communication between computer vision and controls will be done in code with a FIFO system implemented. The code on the left from computer vision creates and writes to FIFO, while the code on the right is used by controls to read it. Conclusion. The controls teams have designed a closed-loop motion control system that implements a PLC and HMI. Our team also is working to ensure communication between the controls and computer vision code is working as intended, in addition to the Jetson board and PLC. Due to the limitations placed upon the Ponderosa group due to the outbreak of COVID-19, tuning the PID controller with the fluids team and the S-motion profile for the solenoids will have to be done in the future. The PCB is currently in development and will be printed once completed.